All right, some more on gravitation. Back in chapter 6, we talked about how if an object was in uniform circular motion, right, if we see that something is in uniform circular motion, then we know that it has an acceleration which is directed inward, and that the magnitude of that acceleration is v squared over r, where v is its speed in this orbit, in this motion, and r is the radius of the motion. So planets or objects that go around, say the sun or the moon going around the earth, these objects are close to uniform circular motion. It depends. Not all of them have perfectly circular orbits, but we can certainly approximate it that way. Certainly the force of gravity is the force which is causing this motion to occur. So there's always to be some force causing your object to follow this path. When we had cars moving around in a circle, there was usually static friction between the tires and the road. You could have a string, which is making something move around. In our uniform circular motion lab, it was a spring that made it move around in a circle. There has to be something which is pulling towards the center, which is causing that circular motion. In the case of objects in space, it's gravity. So looking at sort of a diagram here, say I have my planet, and it's moving around in a circular motion around the sun. It has a radius of that orbit of little r. And so gravity is the force causing this to happen. Its acceleration is the centripetal acceleration. And so this is a very simple F net equation. I just say, well, F net is the force of gravity. I guess I'm saying that this is positive. And that is causing ma, and a is v squared over r. So then I could substitute in this situation, I have capital G, little m, where little m would be the mass of our planet. The mass of the sun, again, I write as capital M with a circle and a dot in it. And then over r squared, where r is the distance between the sun and our planet. And then that has to equal the mass of my planet times v squared over r. And so I can set these things equal to each other. I have an r squared at the bottom of this and an r over here, so I can cancel one of those out, and I have this equation. Now this looks familiar on this side, except I'm missing a 1/2. If I multiply this by 1/2, I have the kinetic energy. If I this side, this is the gravitational potential energy. Not the negative, it's not negative, it's the positive gravitational potential energy, right? This is U sub G, and this is the kinetic energy multiplied by 2. So I multiply both sides by 1/2 to make them really look that way. So this is the kinetic energy. That's the kinetic energy that this object would have as it moves around in its orbit. And that equals the potential energy, negative the potential energy divided by 2. This wasn't specific for any particular planet. This is just any object that's being held in its circular motion by the gravitational force. Any object that's moving in its motion because of a gravitational force, the kinetic energy of that object is going to be negative 1/2 its gravitational potential energy. This is not just true here, but it's also true for any object in a stable orbit, a stable configuration around another big object. This is called the Virial Theorem. This idea that the kinetic energy of an object in a stable orbit or a stable configuration is equal to negative 1/2 its potential energy is called the Virial Theorem. This is not only true for masses moving around the sun or moving around the earth or something like that, but it's also going to be true for bound electrons in atoms or molecules. A bound electron would have kinetic energy equal to negative the potential energy due to electric static force divided by 2. It's a very, very powerful thing called the Virial Theorem. If you see something in a stable orbit, not just a circular orbit, but a stable orbit, you know that its kinetic energy has to equal 1/2 negative 1/2 its potential energy. That, of course, means that if I go in through and calculate its total mechanical energy, the kinetic energy is this. Obviously, the potential energy is that. And so when I add that, I end up with just 1/2 of the potential energy, or Gm, capital M, over 2R, and it's negative. Again, as we see again, the total mechanical energy is negative. This is a bound system. Bound systems have negative total mechanical energy. If they had zero or positive mechanical energy, they wouldn't be bound. The objects would be able to they'd be free from each other. They'd be roaming around. But the bound means that they are sort of stuck together. They're a team. And they go, whatever that happens to one really is going to happen to the other in terms of what the center of mass of that system is going to do. Other thing is this idea of local gravity. So we've never actually derived this, but on the surface of the Earth, this should still be true. We should still have the force of gravity should be equal to, if you have some mass near the surface of the Earth, the gravitational force on it should be capital G, its little mass, times the mass of the Earth, divided by the radius of the Earth squared. We usually just write that as little m times little g. And so that must mean that little g is equal to g, the mass of the Earth, divided by the radius of the Earth squared. And you can actually go through and do that. And when you do that and you plug in the numbers I've given you, you actually end up with 9.82 meters per second squared, which is certainly close enough that we can roll with it. The actual 9.80 and 9.81 are measured values that are sort of more typical actual measurements. But that's where that number comes from, is actually is capital G times the mass of the Earth divided by the radius of the Earth squared. One of the problems I have you do is talking about what if you went inside an object. So as you go inside an object, what's the gravitational force that masses feel as they move inside, as you move deeper? So I'm showing this here. So if this is the actual radius out here of your object, say the Earth, if you're inside, if there's some mass in here, what's the gravitational force on a mass that's located there? What do you do about the fact that you've got some out here which is pulling it, out, but then you have some on the other side which is pulling it in? It turns out if you do the correct integration, which is really what you'd have to do, that only the mass which is interior of R actually produces a gravitational force on this right here. All the mass outside of the radius that you're interested in will actually, the forces from that will cancel out. You can sort of make an argument, the mass that's on this side, it's certainly closer, but there's less of it that would be pulling it in, say, this direction. Whereas, although this mass over here is further away, everything over on this side, there's more of it. And so it actually all integrates away, and all we end up with is the gravitational force from the material, which is interior. And so in this case, it's only the mass which is interior here that produces a gravitational force on material at that radii. So the force due to gravity, if your R is inside the radius of the object you're talking about, would be Gm, or mass is interior, over R squared. How do you determine that interior mass? This is actually part of a problem you are supposed to do. If you assume that you had a constant density, that a uniform density, remember that this is density, that little row, then you could take the mass of your object, the total mass of your object, and divide it by its volume, and that would be the density. So for a sphere, the volume of a sphere is 4/3 pi r cubed. So this is my density, is the total mass of my object divided by the total volume of my object. in order to find the mass interior, I need to multiply that density times the volume, which is interior of little r. So the volume, which is inside of little r, is 4/3 pi little r cubed. And so if I multiply this density times the volume, which is inside, so here's the density, here's the volume interior, and so the 4/3 and the pi's cancel, and what I end up with is the total mass of my object multiplied by a fractional radius cubed. So r over capital R, that tells me how much of the radius, how far inward am I going. If I go halfway in, little r over capital R would be 1/2. If I only go 90% in, then it would be 0.9. And then I cube it because it's a volume, right? Volume is dependent upon r cubed. So the force of gravity, and plug this all in. So for mass interior, right? Mass interior was one of the things in my equation over here. I'm just going to take this equation and I'm going to plug in the mass interior equation I have here. So I have capital G little m over r squared, and then I put in these, cancel stuff out, and I end up with this equation. This is for when r is greater than 0 or equal to 0 and less than and equal to the radius of the actual object. And this is actually part 6. What I just did, that whole little derivation with the density and stuff like that, that's part C of number 25. You can use that for part B for number 25, and then the answer for part A is just your typical part of this object. So number 25, I think you guys can do part A. The f sub g would just be your capital G. You're going to have a mass. The big mass is the entire mass of the thing, which is 1.0 times 10 to the 4. I put a little m because if I put a little m mass near it, and then the radius would be the 1 meter squared. That's the actual. So here I have an object which is 1 meter, and I want to know if I put it out here at 1.5. Oh, sorry, for part A it's 1.5 meters. So I put it at 1.5 meters away. Well, then I'm outside the object. So it's just how far away is it from the center of mass. For part B, I'm going to use the equation I just had. So we've got, oh goodness, it's up here. G, capital M, little m, or big M is the 1 times 10 to the 4. And then I'll put the radius of the actual thing. Well, the radius of the actual thing is 1 meter, and so I cube it, but then I'm at an r of 1/2 a meter. And that's the force of gravity when you're actually inside. So it's basically saying if we have our mass here at 1/2 a meter, again, this is 1 meter in radius, but now it's there. And then the part C is essentially this derivation that I showed above here. I could go over that more in class if we want to on Thursday or even Tuesday next week. All right, there's one last thing in this chapter, which goes back to one of the people who worked before Newton. So before Newton, there was Johannes Kepler, and he absolutely was trying to explain the motion of planets in the sky. Planets do a thing called retrograde motion, where they appear to move backwards in the sky. They do it over a period of weeks, and it turns out this is just an effect of us passing them. Or them passing us. If it's Venus or Mercury, they can pass us as they move, as we all move around, you know, we're on like basically a track, and they move faster around the sun, those Venus and Mercury do, so they pass us. And when they do that, we see their motion relative to the stars in the sky is moving backwards. And so they didn't just, unlike the stars in the sky or the moon or even the sun, which just, they just move forward in the sky. They don't do these weird backwards motion. The planets would have very strange motions, and they were impossible to predict with just a simple orbit around the Earth. And Kepler and Copernicus and them knew it, and so he was trying to explain their motion. They're called wanderers. Anyways, he had 3 laws. He was really the first person to come up with laws that were mathematical in basis to explain any physical phenomenon. This is way before chemists or biologists or anybody else. This is really the beginning of the modern idea of science. And he says planets move in elliptical orbits, and that can be written in a very mathematical way. We're not going to do it here, but they can be written that way. So an elliptical orbit, an ellipse is just a mathematical formula. It's a mathematical shape. It's an oval. Circles can be ellipses, just like a square is a rectangle. So a circle is an ellipse. It's just a very special ellipse, just like a square is a special kind of rectangle. Ellipses have a thing called E, which is their eccentricity, which measures how ovalish they are. A circle has an E equals 0. The maximum eccentricity is, it has to be less than 1, but it could be 0.99. Most planetary orbits are pretty close to circles. Things that have very eccentric orbits are things like comets, where they get really close to the sun, they get further away from the sun. There's all kinds of names for positions of where objects, when they're in their orbits, can be. I've got sort of a drawing of a very sort of eccentric orbit here. So the sun would be, if this was actually talking about an object moving around the sun is going to be at what we call a focus of the ellipse. So ellipses have 2 foci instead of a center, although a circle has both focus at points at the very center. That's sort of what the eccentricity is measuring. So if you look at this orbit, there's places where the object is close to the sun, and there's places where the object is far from the sun. Those are called perihelion. It's the closest approach, and aphelion is the furthest approach. If you are orbiting the Earth instead, like the moon does, you have perigee and apogee, which we hear those terms said a lot. So perigee is the closest approach of something that orbits the Earth, and apogee would be its furthest distance that it can get. Sometimes if you're just talking about other stars, we have periastron and apastron. It's all very Latin sounding. Anyways, so he said that they go around in ellipses, not perfect circles, not all the time. Most orbits are not perfect circles, although perfect circles are mathematically allowed. He also said that a line going from the sun to the planet, so here's a line, that this line, as you followed it for a period of time, so say you followed that for a month, it's going to sweep out this area. If you go and watch the planet at some other period of time, so again from here, so again a line from the sun to the planet, now it's this long line, and you watch it for another month, you'll get another area here. And what he said is that these, if it's an equal amount of time, if it's a month on both ends, then these areas are equal to each other. What that really means is that the planet moves slower when it's further from the sun and faster when it's closer to the sun. What this really, really, really is mathematically, once Newton and all these things got worked out, is the saying about the conservation of angular momentum. It says the angular momentum is conserved. So it's a very early physics sort of equation talking about angular momentum, even though we didn't know what angular momentum was at the time. Essentially, this is L equals mvr. And as as r gets smaller, if r is smaller, then v has to be larger. Over here, r is larger, and so v becomes smaller. And his last law was the law of periods, where he said the time to complete one orbit, we're writing as capital P. Your book actually writes this as capital T, but we abandoned capital T at one point, and we're calling it capital P, so don't freak if my notes look different than their book. That squared is equal to this, which is just a constant, which has to do with, well, it's a constant, except you have the mass of the actual object you're orbiting. So the mass here is actually, this is actually the total mass of both objects. But typically, this is dominated by the larger object. So when you orbit the sun, or even a planet, the mass of the planet is nothing compared to the mass of the sun. Nothing. It's like 1,000,000 times smaller in the case of the Earth. And then how far? So r, which is the radius of the orbit, or if it's a non-circular orbit, it's the average distance that the two objects have during the orbit. This is the only equation where mass is written, which allows us to get the masses of objects in space. Any mass you read for an object in space, especially a solar system sort of object or something like that, we're getting it from this equation. And you can actually get this equation if you go back to this idea of kinetic energy in an orbit and things like that. You can actually rewrite these things, maybe even more specifically this one. If you rewrite this v as r 2 pi r over p and move things all around, you can actually get this equation with rp over there. I'm not going to do it, but that is where that equation comes from. Although actually Kepler's version of this really was more that p squared had to do with r cubed. And the actual numbers inside there, he was less specific with. In any case, we can use this for number 45. It tells me, I'll go ahead and do this whole one. It tells me that the radius of the orbit, so we have a little, Mars has got two tiny little captured asteroids, which are moons. Satellite. It's not a satellite to an astronomer. It doesn't necessarily mean it has to be an artificial satellite. It could just be anything that orbits. It usually means something that's not so big, and that's true in the case of Phobos. So Phobos moves on a circular orbit where its radius is 9.4 times 10 to the 6 meters from the center of Mars, and the period of its orbit is 7 hours and 39 minutes. Well, I need that in seconds. So I'm going to convert that to seconds, just a second. All right, so I just did the 7 hours times 36, right? This is 7 hours times 3,600 seconds in an hour plus 39 times 60 seconds in a minute. And that's where I get that number. And I'm going to use this equation. So p squared is equal to 4 pi squared gm r cubed, and I want to solve for mass. So if I move that all around, I end up with 4 pi squared g p squared r cubed. I essentially just cross multiply the p squared and the m and get it there. And if I put all my numbers in, I get 6.48 times 10 to the 23 kilograms. Now, it comes to masses of objects, especially planets. So this is the mass of Mars. That seems like a lot. It's like, wow, that's 10 to the 23 kilograms. It seems like a lot. But typically, we try to compare planets' masses to other planetary masses. So if we go back and we look at, way back here, the mass of the Earth. Mass of the Earth is 5.98 times 10 to the 24. And so typically we write masses of objects in terms of other planets. So if I convert, I can divide that by 5.97 to the 24. Is that right? I just saw it and then I totally... 5.98 times 10 to the 24. And I get that that's only 0.11 times the mass of the Earth. So it's only about 11% the mass that the Earth is. And that's much more physical to us. And so when we talk about these really big objects like planets, you know, if you look at their number, it's overwhelming. You're like, it seems like a lot. But if you compare it to things like the Earth, then we have a better feel for it. So planets that are like the Earth, like Mars or Venus and Mercury, we'll compare its mass and we'll write it in terms of Earth masses. If it's a bigger planet, we'll compare it and write it in terms of Jupiter masses. Stars, we write all stellar masses based upon how much more or how much less is it than the sun's mass. So, you know, everything has a unit that goes, it makes it more understandable, more physical. Rather than using kilograms, typically we talk about how much is this like the Earth, or how much is it like Jupiter, or how much is it like other stars. All right, that's all for chapter 13. I'm going to hold off on chapter 14 until next week.